Let's start. Number 15. The cool beneath the stone. Approximately 4,000 years ago, in the volcanic plateau of central Anatolia, someone descended into a hole in the ground and did not come back up for a very long time. Not because they were trapped. Because down there, the air was cool. The Derinkuyu underground city in modern-day Turkey extends approximately 85 meters below the surface of the Cappadocian Plateau. It contains at least 18 levels of tunnels, chambers, storage rooms, ventilation shafts, and communal spaces carved directly into the soft volcanic tuff deposited by ancient eruptions of Mount Erciyes. The complex could shelter an estimated 20,000 people along with their livestock and food supplies. The walls were carved with stone tools, widened over centuries by successive generations who understood something about thermodynamics that would not be formally described for another 3 millennia. Below the surface, the temperature holds steady at roughly 13 to 15 degrees Celsius year-round. Above ground, the Anatolian Plateau routinely exceeds 40 degrees Celsius during summer months. That is a 25-degree differential created entirely by depth. No mechanical system. No energy input. Just rock and gravity and the thermal inertia of the Earth itself. Ömer Aydan, a geotechnical engineer at the University of the Ryukyus in Japan, published an analysis in 2004 examining the structural engineering of Cappadocian underground settlements. His research concluded that the ventilation shaft system was not accidental. The builders had positioned vertical air channels at calculated intervals to create passive convection currents. Warm air rising through the shafts pulled cooler subterranean air through the lower chambers, producing continuous airflow without any mechanical assistance. This is the same thermodynamic principle used in modern passive cooling architecture. These builders applied it with chisels and firelight. However, the truly remarkable dimension of Derinkuyu is not the engineering. It is what it implies about the relationship between heat and civilization. The Hittite texts from the 2nd millennium BCE reference underground refugia in the Cappadocian region. The early Christian communities who expanded the tunnels during the Byzantine era inherited a technology that was already ancient when they arrived. The original builders left no written record. Their names are gone. Their language may be extinct. Yet the tunnels they carved remain at a constant 13 degrees, while the surface above blisters in the July sun. Could you carve a city into stone with nothing but hand tools? The people who built Derinkuyu could. And they did it because staying above ground during the worst heat months would have killed them. Number 14. Thread from the desert. Approximately 7,000 years ago, along the banks of the Nile in what is now pre-dynastic Egypt, someone pulled fibers from the stem of the flax plant, twisted them into thread, and wove a fabric so fine that individual threads were nearly invisible to the naked eye. This was not decorative craft. This was thermal engineering worn on the body. Linen, produced from the cellulose fibers of Lenum usitatissimum, possesses a combination of properties that no other natural textile matches for heat survival. The fibers are hollow, creating microscopic air channels that wick moisture away from the skin at rates significantly faster than cotton or wool. Linen absorbs up to 20% of its own weight in moisture before feeling damp to the touch. In dry heat, this absorbed moisture evaporates from the fabric surface, producing a measurable cooling effect against the skin through the same thermodynamic process that makes sweat effective. Gillian Vogelsang Eastwood, a textile archaeologist and former director of the Textile Research Center in Leiden, published extensive analyses of ancient Egyptian linen technology. Her research documented thread counts in some recovered fragments that exceeded 200 threads per inch, a density comparable to high-end modern dress shirts. The spinning and weaving technology required to achieve this density using hand tools demanded extraordinary skill and patience. A single garment could require weeks of labor. Therefore, linen was not simply clothing. It was survival technology with a production cost so high that its distribution reveals the social hierarchies of ancient heat-stressed societies. The finest linen went to elites, priests, and pharaohs. Coarser weaves clothed laborers. The dead were wrapped in it because the properties that kept the living cool also slowed decomposition of the deceased. Every mummy in the Valley of the Kings wears a testament to a textile technology invented specifically to keep human bodies functional in temperatures that routinely exceeded 45 degrees Celsius. What makes this survival method particularly relevant today is that modern synthetic fabrics still struggle to match linen's thermoregulatory performance. A 2019 study conducted by researchers at RMIT University in Melbourne measured the microclimate between fabric and skin across multiple textile types and found that linen maintained the lowest skin surface temperature under controlled heat exposure. A fiber developed 7,000 years ago in the Nile Delta still outperforms fabrics designed in laboratories with access to polymer chemistry and computer modeling. Every linen shirt hanging in a closet today traces its ancestry to a desert civilization that understood something fundamental about surviving heat. The fabric breathes because the people who invented it could not afford for it not to. Number 13. The fire that cools. Approximately 65,000 years ago, on the Australian continent, someone set the landscape on fire, deliberately. Not to destroy, to cool. Aboriginal Australian fire management, known as cultural burning or cool burning, represents arguably the longest continuous land management practice in human history. The technique involves setting low-intensity fires during cooler months to clear undergrowth, reduce fuel loads, and create a mosaic of burned and unburned patches across the landscape. The fires burn at ground level, moving slowly through dry grass and leaf litter without reaching the canopy. The burned patches green up first when rains arrive, creating food sources that attract game. The unburned patches retain shade cover and moisture. The cooling function operates on multiple levels. Dense, unmanaged bush accumulates dead organic matter that absorbs and radiates solar heat. A landscape choked with dry fuel can register ground surface temperatures 10 to 15 degrees higher than land that has been recently cleared by controlled fire. After a cool burn, the dark ash absorbs initial solar radiation, but the rapid regrowth of green vegetation creates a living canopy that reflects far more sunlight than dead brown undergrowth. The net thermal effect is a cooler landscape surface. In 2020, researchers at the University of Tasmania, led by David Bowman, published findings in Nature, Ecology and Evolution, demonstrating that Aboriginal fire management practices had measurably altered the vegetation structure, fire regime, and thermal characteristics of the Australian landscape over tens of thousands of years. The research suggested that the cessation of traditional burning after European colonization directly contributed to the catastrophic bushfire conditions that now characterize Australian summers. The landscape had been managed. When the management stopped, the heat returned. Yet fire management was only one layer of an integrated thermal survival system. Aboriginal peoples across the arid interior of Australia developed behavioral thermal regulation strategies refined over thousands of generations. Activity was concentrated in the cooler hours of early morning and late evening. The hottest part of the day was spent in shade, often in shallow depressions scooped into sand beneath trees where contact with cooler subsurface soil lowered body temperature. Body painting with clay and ochre mixtures created a reflective layer on the skin that reduced solar heat absorption. The humans who managed fire to cool a continent were not reacting to heat. They were engineering an entire ecosystem's thermal profile across geological time. Modern climate scientists are only now beginning to understand what Aboriginal Australians practiced for 65,000 years. Number 12. Moving with the moon. Approximately 8,000 years ago, across the Western Sahara, the rain stopped. Not suddenly, not in a single season. The African humid period, a climatic phase that had transformed the Sahara into a grassland dotted with lakes, rivers, and permanent human settlements, began its collapse around 500 years ago. Over the next 2,000 years, the world's largest desert reasserted itself. Lake Megachad, which had once covered an area roughly the size of modern Germany, shrank to a fraction of its former extent. Rivers that had supported fishing communities dried into sand channels. The grasslands that fed cattle herds turned to rock and dust. The humans who lived through this transition did not simply die, they adapted. And the most fundamental adaptation was temporal. They reversed the relationship between day and night. Saharan nomadic peoples, ancestors of the modern Tuareg, Tubu, and Berber populations, developed a survival system organized entirely around darkness. Travel occurred at night, when surface temperatures dropped from daytime highs of 50 degrees Celsius to nighttime lows of 15 to 20 degrees. Navigation relied on stellar positioning, wind direction, sand texture underfoot, and accumulated generational knowledge of terrain features identifiable by moonlight or starlight. Camps were established before dawn and dismantled after sunset. The metabolic logic was precise. Walking in 50-degree heat, a human body requires roughly 6 to 9 liters of water per day to maintain hydration through sweat-based cooling. Walking at night, when evaporative water loss drops dramatically, the same journey requires approximately 2 to 3 liters. In a landscape where the nearest water source might be 80 kilometers away, that difference is the difference between arriving alive and collapsing 30 kilometers short. Nikolaus Borowka, a researcher at the German Archaeological Institute, published extensively through the 2010s on Saharan adaptation strategies during the aridification period. His work documented seasonal migration routes, stretching hundreds of kilometers between residual water sources, all timed to nocturnal travel windows. The routes were encoded in oral traditions that functioned as navigational databases, storing information about distance, terrain, water quality, and seasonal availability across landscapes that contained almost no permanent visual landmarks during daylight. What would you do if the sun itself became lethal? The people who survived the Saharan collapse already knew. They gave the day to the sun and claimed the night for themselves. Number 11. The jar that sweats. Approximately 600 years ago, in what is now the Nile Delta region of Lower Egypt, someone placed a smaller clay pot inside a larger one, packed wet sand between them, and watched the temperature inside the smaller vessel drop by 15 degrees within hours. This is the Zir pot, two unglazed ceramic vessels, one nested inside the other, with a layer of wet sand filling the gap between them. As water in the sand evaporates through the porous outer wall, it absorbs thermal energy from the inner vessel. The process is identical to how human sweat cools the skin. The result is a passive refrigeration system capable of reducing interior temperatures from roughly 40 degrees Celsius to approximately 25 degrees, powered entirely by evaporation and requiring no energy input beyond occasional addition of water to the sand layer. Archaeological evidence from the Old Kingdom period, roughly 2600 BCE, documents ceramic vessel configurations consistent with evaporative cooling technology. Muhammad Ba Abba, a Nigerian teacher, received the Rolex Award for Enterprise in 2001 for reintroducing the Zir pot design in rural northern Nigeria, where it extended the shelf life of tomatoes from 2 days to 21 days and eggplants from 3 days to 27 days. His work demonstrated that a technology invented in the Bronze Age remained more effective than any available alternative for food preservation in off-grid communities. However, the Zir pot was only the most portable version of a broader evaporative cooling tradition. Ancient Egyptian houses incorporated shallow pools of water in central courtyards. The evaporation from these pools cooled the air flowing into surrounding rooms. Wet reed mats hung across doorways and windows served the same function, turning every breeze into a natural cooling system. The pharaonic palaces at Amarna, built by Akhenaten around 1350 BCE, featured architectural elements consistent with deliberate evaporative cooling design, including open-air ventilation channels aligned with prevailing winds and water features positioned to maximize airflow across wet surfaces. The principle is embarrassingly simple. Water absorbs heat when it changes from liquid to vapor. Direct that process through the walls of a container, across a doorway, or over the surface of a pool, and the surrounding air temperature drops measurably. No compressor. No refrigerant. No electricity, just clay, water, and an understanding of phase change thermodynamics that predated the formal discovery of latent heat by 4,000 years. Does it bother you that a Bronze Age farmer in the Nile Delta solved a cooling problem with 2 clay pots and some sand that modern engineers need complex machinery to replicate? It should, because the physics hasn't changed. We just forgot the simple version. Number 10. Written in the bones. Approximately 70,000 years ago, a mutation occurred in the EDAR gene of a population living in what is now East Asia. The mutation, known as EDAR-V370A, altered the protein responsible for developing hair follicles, sweat glands, and tooth structure. Among its effects, it increased the density of eccrine sweat glands across the skin surface. Humans are already the most prolific sweaters in the animal kingdom. An average adult possesses between 2 and 4 million eccrine sweat glands, capable of producing up to 12 liters of sweat per day under extreme exertion. This is not a minor biological feature. It is the primary reason humans can function in temperatures that incapacitate nearly every other large mammal on the planet. A horse overheats after sustained running in moderate heat. A dog can only cool itself through panting, which becomes ineffective above 35 degrees Celsius. A human, drenched in sweat from head to foot, can walk through 45-degree heat for hours if adequately hydrated. Partecipetti at Harvard University published research in 2007 identifying the EDAR variant as one of the strongest signals of positive natural selection in the human genome. The mutation spread through East Asian populations with a speed that indicates intense selective pressure. Individuals carrying the variant survived and reproduced at significantly higher rates than those without it. The thermal advantage of denser sweat glands in hot, humid environments may have been one driver of that selection, alongside other effects of the gene on hair thickness and mammary gland development. Therefore, the genetic architecture of heat survival is not hypothetical, it is measurable, it is mapped. And it tells a story of populations that endured heat so extreme that their bodies were permanently rewritten by the experience. The EDAR 5370A variant is carried today by roughly 93% of East Asian populations, 70% of Native American populations, and fewer than 5% of European and African populations. The distribution is a fossil record of thermal pressure, written not in stone but in DNA. Melanin tells a parallel story. Populations that inhabited equatorial regions for tens of thousands of years carry genetic variants that maximize melanin production, creating a biological sunscreen that reduces UV radiation damage to underlying tissue. The MC1R gene, which regulates melanin synthesis, shows among the strongest signatures of natural selection in populations originating from high UV environments. Darker skin reduces the risk of folate degradation caused by ultraviolet exposure, and folate deficiency during pregnancy dramatically increases the risk of neural tube defects. The selective pressure was reproductive. The populations that could not protect their folate reserves had fewer surviving offspring. Over thousands of generations, the genome adjusted. You carry the thermal engineering of your ancestors in every cell. The shade of your skin, the density of your sweat glands, the efficiency of your cooling system. All of it was built by heat. All of it was paid for in generations of people who survived temperatures that killed those without the right mutations. Number 9. Cities that breathe. Approximately 3,000 years ago, in the desert city of Yazd in central Iran, someone built a tower designed to catch wind that did not yet exist. The bajir, or windcatcher, is a passive ventilation structure that rises above the roofline of a building and channels external air downward into the interior living spaces below. The simplest designs feature a single opening facing the prevailing wind direction. The most sophisticated versions, including the tower still standing in Yazd today, feature 4 or 8 directional openings that capture wind from any direction and funnel it through internal channels lined with adobe or fired brick that absorb heat from the incoming air before it reaches the occupied rooms below. The cooling mechanism operates on 2 principles simultaneously. First, as wind enters the tower and descends through narrow channels, it accelerates. Faster-moving air feels cooler on the skin because it increases the rate of evaporative heat loss from the body. Second, the thermal mass of the tower's thick walls absorbs solar heat during the day and radiates it outward at night. During the daytime, when cooling is needed most, the walls are still releasing the cooler nighttime temperature into the passing air column. The incoming air is actively chilled by the masonry itself. Anna Porbacher at the University of Tehran published a 2018 study measuring the temperature differential produced by traditional Badger towers in Yazd. Her research found that the towers reduced indoor air temperature by 8 to 12 degrees Celsius compared to external conditions during peak summer heat. In a city where summer temperatures regularly exceed 45 degrees Celsius, that reduction brings interior spaces below the 35-degree threshold, at which sustained human habitation becomes physiologically viable without modern air conditioning. Yet the Badger was never a standalone technology. In many traditional Iranian homes, the windcatcher tower sits directly above an underground chamber called a shabastan, which connects to a qanat, an underground water channel. Air descending through the tower passes over the surface of the qanat water before entering the living space. The evaporative cooling from the water surface drops the air temperature by an additional 5 to 8 degrees. The combined system, tower plus underground chamber plus water channel, could produce interior temperatures below 25 degrees Celsius, while the desert surface above shimmered at 50. The architects who designed these systems never wrote equations for convective heat transfer. They never calculated Reynolds numbers or evaporation rates. They built, observed, refined, and transmitted the knowledge through apprenticeship traditions that persisted for millennia. The towers in Yazd still work. They have been working for 1,000 years. They will continue working long after the last air conditioning compressor on Earth has rusted into silence. Number 8. Water from stone. Approximately 200 years ago, in the Negev desert of what is now southern Israel, the Nabatean civilization built a city called Avdat on a rocky plateau that received less than 100 millimeters of rainfall per year. For comparison, the Sahara Desert receives roughly the same amount. London receives approximately 600 millimeters. The Nabateans looked at this arid wasteland and saw a functioning water supply. The key was runoff harvesting. The Negev limestone surface is largely impermeable. When rain does fall, it runs off the rocky slopes rather than soaking into the ground. The Nabateans constructed elaborate channel systems that captured this runoff and directed it into underground cisterns carved into the bedrock. A single well-positioned cistern could collect thousands of liters from a rainfall event that lasted minutes. The channels were graded at precise angles to maximize flow velocity without causing erosion, and the cistern openings were designed to filter debris while admitting maximum water volume. Yoav Avni at the Geological Survey of Israel published research in 2006 demonstrating that the Nabatean water system in the Negev was capable of supporting agricultural production and a permanent population of approximately 30,000 people in a landscape that, without the infrastructure, could sustain fewer than 500 pastoral nomads. The multiplication factor was extraordinary, 60 times more people living in a desert because of engineering. However, the cisterns served a dual survival function beyond hydration. The underground chambers, carved into bedrock at depths of 5 to 10 meters, maintained temperatures of roughly 18 to 20 degrees Celsius regardless of surface conditions. These spaces functioned as cooling refugia during the most extreme heat events. Archaeological evidence from Avdat and the nearby city of Shivta reveals residential architecture designed to channel daily activities from above-ground spaces during cooler hours to below-ground spaces during peak heat, a vertical migration pattern within the architecture itself. The Nabateans controlled the incense trade routes connecting Arabia to the Mediterranean. Their wealth came from commerce. Their survival came from water engineering so precise that modern hydrologists study it for application in contemporary arid land management. A civilization that flourished in one of the most hostile thermal environments on Earth for over 500 years, using nothing but stone, gravity, and an obsessive understanding of where water goes when it rains for 11 minutes per year. What would you build if you had 100 millimeters of rain and 300 days of lethal sun? The Nabateans built an empire. Number 7. The collapse that built Egypt. Approximately 500 years ago, the Sahara was green. It had been green for roughly 6,000 years. Lakes filled depressions across what is now the most inhospitable desert on the planet. Hippopotamuses swam in waters that today are buried under 50 meters of sand. Cattle herders grazed livestock on grasslands stretching from the Atlantic coast to the Nile. Rock art in the Tassili Najjar Mountains of modern Algeria depicts swimmers, boats, and fishing scenes in a landscape that now receives less than 20 millimeters of rain per year. Then the rain stopped. The end of the African humid period, driven by a gradual shift in the Earth's axial precession that altered the West African monsoon pattern, converted the Green Sahara into the hyper-arid desert we recognize today over a period of roughly 2,000 years. Peter Domenical at the Lamont Doherty Earth Observatory published a landmark 2000 study in Quaternary Science Reviews analyzing ocean sediment cores from the Atlantic coast of West Africa. The cores revealed a dramatic increase in wind-blown Saharan dust deposits beginning around 500 years ago, corresponding precisely with the onset of aridification. The dust layers thickened progressively over centuries, recording the slow death of an entire biome in the sediment of the Atlantic seafloor. The human response was migration on a continental scale. The cattle-herding populations of the Central and Western Sahara moved east and south. Many converged on the Nile Valley, the last remaining permanent water source in the region. The concentration of displaced populations along the Nile created the demographic pressure that many researchers, including Fakhri Hassan at University College London, argue is a direct catalyst for the emergence of organized Egyptian civilization. The irrigation systems, centralized grain storage, hierarchical administration, and monumental architecture that characterize pharaonic Egypt may not have been invented by people who chose to live in the Nile Valley. They may have been invented by refugees who had nowhere else to go. The implications are staggering. The civilization that built the Great Pyramids, that invented hieroglyphic writing, that created one of the most enduring cultural traditions in human history, may owe its existence to a heat catastrophe that made everywhere else uninhabitable. The Sahara did not just kill a way of life, it concentrated the survivors into a narrow strip of irrigable land and forced them to cooperate or die. They cooperated. And from that cooperation emerged a civilization that lasted 3,000 years. Does knowing that ancient Egypt may have been founded by climate refugees change how you think about what civilizations are? They are not chosen. They are forced into existence by the pressure to survive. Number 6. Mud that outlasts concrete. Approximately 800 years ago, in the floodplain of the Bani River in what is now central Mali, builders constructed a mosque from mud, not a small mud hut. A structure spanning 75 meters in length and 75 meters in width, rising to a height of 20 meters, with walls up to 60 centimeters thick and 3 massive minarets visible across the savannah. The Great Mosque of Djenné is the largest mud brick structure on Earth, and it is a cooling machine. Adobe and Banco construction, using sun-dried bricks made from a mixture of clay, sand, water, and organic fiber such as rice husks or straw, creates walls with extraordinary thermal mass. Thermal mass is the ability of a material to absorb, store, and slowly release heat energy. A thick mud wall absorbs solar heat during the day, but releases it so slowly that the interior of the structure remains cool until well after sunset. By the time the stored heat has migrated through 60 centimeters of dense earth and begun warming the interior, the exterior temperature has already dropped. The wall then begins absorbing cool nighttime air, reversing the cycle. Ronald Rael, a professor of architecture at the University of California, Berkeley, published research in 2009 examining the thermal performance of traditional earthen construction in the Sahel region. His findings demonstrated that interior temperatures in well-constructed mud buildings remain 12 to 15 degrees Celsius below exterior peak temperatures during the hottest months. A building that maintains 30 degrees inside while the outside air registers 45 is not comfortable by modern standards. It is survivable. And in a region where modern air conditioning is unavailable to the vast majority of the population, survivable is everything. Yet the most remarkable aspect of Saharan and Sahelian mud architecture is its integration with community. The Great Mosque of Djenné requires annual replastering, a festival called the crépissage, that involves the entire community in a collective act of architectural maintenance. The mud walls erode in the rainy season and must be rebuilt in the dry season. This annual cycle binds the building to the community that uses it in a relationship of mutual dependency. The building cannot survive without the people. The people cannot survive the heat without the building. The Romans poured concrete, the Egyptians cut limestone. The people of the Niger River Delta scooped mud from a riverbank and built structures that kept their children alive through 45-degree summers for 8 centuries. The technology requires no factory, no supply chain, no specialized materials. It requires only earth, water, and the knowledge of how to shape them. That knowledge has been transmitted from builder to builder across generations, in a chain of survival wisdom that stretches back thousands of years into the deep history of the Sahel. Number 5. The 300-year drought. Approximately 200 years ago, something shifted in the climate systems of the eastern Mediterranean, the Middle East, and South Asia simultaneously. Rainfall declined, rivers shrank, harvests failed, and within roughly 200 years, three of the most advanced civilizations on Earth collapsed. The Akkadian Empire, the first empire in recorded history, ruled Mesopotamia from approximately 2334 to 2154 BCE. At its peak under Sargon of Akkad, it controlled territory stretching from the Persian Gulf to the Mediterranean coast. The empire depended on rain-fed agriculture across the fertile plains of northern Mesopotamia. When the rain stopped, the agricultural system collapsed. Cities were abandoned. Populations fled south toward the irrigated zones of southern Mesopotamia. A wall was built across the Tigris-Euphrates plain to keep the starving northerners from overwhelming the southern cities. The texts that survive from this period describe famine, displacement, and social disintegration. Harvey Weiss at Yale University published the foundational research on the 4.2 kiloyear event in 1993 in the journal Science. His team analyzed soil samples from Tel Leilan in northeastern Syria and documented a layer of wind-blown dust, sterile of any biological material, covering the ruins of the Akkadian settlement. The dust layer corresponded to a period of severe aridification lasting approximately 300 years. Weiss proposed that a mega-drought, driven by shifts in atmospheric circulation patterns, simultaneously struck multiple regions across the northern hemisphere. The evidence supported him. In Egypt, the Old Kingdom, the civilization that built the Great Pyramids at Giza, entered a period of political fragmentation and famine around the same time. Nile flood levels, reconstructed from sediment deposits and ancient texts, dropped significantly during this period. Low floods meant reduced irrigation. Reduced irrigation meant crop failure. Crop failure meant the collapse of the centralized state that depended on agricultural surplus to feed its bureaucracy, its army, and its construction workforce. In the Indus Valley, the mature Harappan civilization, which had built the planned cities of Mohenjo-Daro and Harappa with indoor plumbing and standardized brick construction, began its decline around 3,900 years ago. Liviu Giosan at the Woods Hole Oceanographic Institution published research in 2012 suggesting that the weakening of the South Asian monsoon reduced river flow to the point where the Indus Valley agricultural system could no longer support urban populations. The cities did not die violently, they emptied slowly as people dispersed into smaller settlements that required less water. 3 civilizations, 3 continents, 1 drought. The 4.2 kiloyear event is now formally recognized as a geological boundary, marking the transition from the Middle to the Late Holocene. It is the only climatic event to define a geological epoch boundary based on its impact on human civilization, rather than on geological or biological criteria. The International Commission on Stratigraphy ratified this designation in 2018. The mechanisms that drove the 4.2 kiloyear drought, shifts in atmospheric circulation, changes in sea surface temperature patterns, and disruptions to monsoon cycles, are the same mechanisms that contemporary climate models identify as active risks in the current century. The drought that ended the Bronze Age's first act is not ancient history. It is a case study in what happens when heat and aridity overwhelm the agricultural systems that civilizations depend on. Could 3 modern civilizations collapse simultaneously from a 300-year drought? The geological record says it has already happened once. Number 4. The Invisible River. Approximately 3,000 years ago, in the arid plateau of eastern Iran, someone dug a tunnel into the base of a mountain, followed the water table downhill for over 70 kilometers, and delivered a steady flow of cold, clean water to a desert settlement that received almost no rainfall. This is the Qanat, a gravity-fed underground aqueduct that taps groundwater at a source elevation and transports it through a gently sloping tunnel to lower-lying settlements. The construction method is precise and dangerous. A vertical shaft is sunk at the source point to reach the water table. Additional vertical shafts are sunk at intervals of 20 to 50 meters along the planned tunnel route, both for ventilation and to allow excavated material to be hauled to the surface. Workers then connect the shafts by tunneling horizontally, maintaining a gradient of roughly 1 to 1.5 meters per kilometer just enough to keep the water flowing by gravity without eroding the tunnel floor. The oldest confirmed qanats in Iran date to approximately the early 1st millennium BCE, though some researchers argue the technology is older. Dale Lightfoot at Oklahoma State University published a comprehensive review of qanat technology in 2000, documenting over 37,000 qanat systems across Iran, with a combined tunnel length exceeding 270,000 kilometers. That is roughly two-thirds the distance from the Earth to the Moon, built with hand tools, in darkness, by workers who dug through rock and soil at the constant risk of tunnel collapse. However, the qanat was not simply a water delivery system. The tunnels themselves functioned as cooling infrastructure. Air flowing through the underground channels was chilled by contact with the surrounding earth and the cold water surface. Traditional Iranian architecture positioned the qanat outlet beneath a central courtyard or basement chamber, where the cold air emerging from the tunnel reduced ambient temperatures by 5 to 10 degrees Celsius. In combination with a windcatcher tower drawing hot air out of upper stories while the qanat pushed cold air into lower ones, the integrated system produced indoor climates that rivaled modern air conditioning in their effectiveness. The genius of the qanat is its sustainability. Because it taps the water table through gravity alone, it cannot overdraw the aquifer the way a mechanical pump can. The flow rate is limited by the natural recharge rate of the groundwater source. A qanat that was properly constructed 1,000 years ago delivers the same volume of water today as it did on the day it was completed, provided the aquifer has not been depleted by modern extraction methods. Many have been. The ancient systems are dying because modern pumps are draining the water tables they depend on, in months that took centuries to fill. If the pumps fail, the qanats will be the last water system standing. They have outlasted every empire that built them. They will outlast the one that is destroying them. Number 3. The uphill escape. Approximately 10,000 years ago, in the highlands of what is now Ethiopia and Kenya, pastoral communities developed a survival rhythm synchronized to the vertical geography of the East African Rift. The principle was simple: heat rises, cool air sinks. At every 1,000 meters of altitude gained, ambient air temperature drops by approximately 6.5 degrees Celsius. A settlement at 500 meters elevation on the floor of the Rift Valley might experience daytime temperatures of 40 degrees Celsius during the dry season. A camp at 500 meters on the adjacent highland plateau, less than 50 kilometers away by walking distance, sits at roughly 27 degrees. The difference between heat exhaustion and comfort, bridged by a single day's vertical migration. This practice, known as vertical transhumance, organized entire societies around seasonal movement between lowland dry season pastures and highland wet season grazing zones. The livestock, primarily cattle, goats, and later camels, could not survive extended exposure to lowland heat during the hottest months. The humans who depended on those animals could not survive without them. Therefore, when the heat climbed, the entire community climbed with it. Diane Gifford Gonzalez at the University of California, Santa Cruz published research in 2017 tracing the origins of East African pastoralism through archaeological and genetic evidence from Holocene sites across the Rift Valley and the Kenyan highlands. Her work documented the emergence of a mobile pastoral system that exploited altitudinal variation to maintain livestock health across seasonal temperature extremes. The system required precise ecological knowledge, including understanding of grass growth cycles at different elevations, water source availability along migration corridors, and disease risk zones where tsetse fly habitat intersected with cattle routes. The cognitive infrastructure required to manage vertical transhumance was formidable. A community elder coordinating a seasonal move had to account for the current condition of highland pastures, the water levels of springs along the route, the timing of rainfall that would trigger grass regeneration, the disease exposure risk for livestock at each altitude band, and the social relationships with groups already occupying the highland zones. A miscalculation in any of these variables could result in livestock death, which, in a pastoral society, meant famine. Modern Maasai, Samburu, and Borana communities in Kenya and Ethiopia continue practicing vertical transhumance today. Their seasonal movements follow routes that may have been in continuous use for thousands of years, refined by observation and transmitted through oral tradition, with a precision that satellite-based rangeland management systems are only now beginning to replicate. The mountains were the original air conditioning. You did not cool the air, you walked to where the air was already cool. And the people who figured this out built entire civilizations on the slopes. Number 2. The lake that vanished overnight. Approximately 200 years ago, a glacial lake the size of the Black Sea drained into the North Atlantic in a matter of months. The event, now known as the 8.2 kiloyear event, triggered a cascading climate disruption that forced agricultural communities across the Middle East and Mediterranean to reinvent how they survived heat, drought, and environmental unpredictability. Lake Agassiz Ojibwe, a massive glacial meltwater lake covering much of modern Manitoba, Ontario, and parts of Minnesota, had been dammed behind the retreating Laurentide ice sheet since the end of the last glacial period. Around 200 years ago, the ice dam failed catastrophically. An estimated 163,000 cubic kilometers of fresh water, roughly equivalent to 40 Lake Superiors, poured into Hudson Bay and from there into the North Atlantic. The sudden injection of cold fresh water disrupted the Atlantic meridional overturning circulation, the oceanic conveyor belt that transports warm water from the tropics to northern Europe. The result was a paradox. The initial effect was cooling in the North Atlantic region, with temperatures in Greenland dropping by approximately 3 to 6 degrees Celsius within decades. Yet the disrupted ocean circulation simultaneously weakened the monsoon systems that delivered moisture to the Mediterranean, the Middle East, and North Africa. While Northern Europe shivered, the Fertile Crescent dried. Richard Alley at Penn State University published the definitive early research on the 8.2 kiloyear event in 1997, based on Greenland ice core data from the GISP2 project. Subsequent research by Bernhard Vininger at the University of Cologne connected the climate disruption to documented archaeological evidence of settlement abandonment, population movement, and cultural change across the eastern Mediterranean between roughly 400 and 8,000 years ago. The survival response was remarkable. Neolithic farming communities in the Levant and Anatolia, which had developed some of the world's earliest agricultural systems during the preceding warm, wet centuries, faced conditions their grain crops could not tolerate. Some communities abandoned farming entirely and reverted to mobile foraging strategies. Others relocated to river valleys and lake shores, where residual water supplies could sustain irrigated agriculture on a smaller scale. The archaeological site of Catalhoyuk in central Turkey, one of the earliest known urban settlements, shows evidence of dietary shifts during this period, with increased reliance on wild plants and hunted game suggesting that the agricultural surplus the settlement depended on had failed. What makes the 8.2 kiloyear event profoundly relevant is the speed. The climate shifted within decades. Communities that had invested generations in building permanent settlements, developing crop varieties, and establishing trade networks had to adapt or collapse within a single human lifetime. Some adapted, some collapsed. The ones that adapted carried the lesson forward: resilience, diversification, water storage, crop variety. The survival toolkit that emerged from the 8.2 kiloyear event became the foundation of every subsequent agricultural civilization's approach to climate risk. The lake that vanished in months rewired human civilization for millennia. The adaptations it forced are still visible in how we grow food, store water, and plan for the possibility that the climate we know could change faster than we expect. Number 1. Why they survived. Approximately 300,000 years ago, on the sun-blasted savanna of East Africa, a species began doing something that no other animal on the planet had ever done. It shared water with individuals who were not its offspring. Every survival method on this list, the tunnels, the towers, the cisterns, the migration routes, the ceramic vessels, the textile engineering, all of them required cooperation. Not the instinctive cooperation of ants following chemical signals or wolves hunting in coordinated packs driven by hierarchy and hunger. Deliberate, negotiated, socially enforced cooperation between individuals who chose to share resources they could have kept for themselves. A qanat cannot be dug by one person. The tunnel systems that watered Persian cities required teams of workers operating in shifts over months or years, supported by communities that fed and housed them during the construction. A windcatcher tower represents the accumulated architectural knowledge of generations, transmitted from master builder to apprentice through traditions that required trust, patience, and the shared belief that investing effort in a structure you might never personally use was worth doing because someone else would benefit. The Nabateans' cistern networks of the Negev were communal infrastructure. The water they collected belonged to the settlement, not to the individual who dug the channel. The Aboriginal fire management practices that cooled an entire continent operated on a landscape scale that no single family or clan could maintain alone. The seasonal migrations of East African pastoralists required coordination between multiple groups, sharing overlapping grazing territories, negotiating access through social relationships maintained across generations. Robin Dunbar at the University of Oxford published decades of research on the relationship between brain size, social group complexity, and cooperative behavior in primates. His work suggests that the expansion of the human neocortex, which accelerated dramatically in Homo sapiens between 300,000 and 100,000 years ago, was driven primarily by the cognitive demands of managing increasingly complex social relationships. The brain did not grow larger to solve engineering problems. It grew larger to solve social ones. The engineering followed. Kim Hill and Robert Boyd, working separately at Arizona State University and the University of California, Los Angeles, published research through the 2000s and 2010s demonstrating that human-scale cooperation, the willingness to share food, water, and shelter with non-relatives, is virtually unique among mammals. Other primates share within immediate family groups. Humans share across families, across clans, across communities, and in times of extreme stress, across ethnic and linguistic boundaries. This capacity is not altruism in the romantic sense. It is thermal insurance. The group that shares water survives the drought. The group that hoards it watches its members die one by one until there are too few left to maintain the infrastructure that kept them alive. The oldest human burial sites, dating to roughly 100,000 years ago, contain evidence of individuals who survived severe injuries and disabilities that would have killed them without sustained care from others. A broken femur that healed means someone carried food and water to the injured person for weeks. A jaw abscess that resolved means someone prepared soft food for a person who could not chew. A child with a congenital deformity who lived to adulthood means an entire community chose to support an individual who consumed resources without being able to contribute labor. This is what separates us, not our thumbs, not our tools, not our language, though all of those matter. What separates us is the willingness to keep someone alive who cannot keep themselves alive. Because we understand, at some level, encoded deeper than reason, that survival is a collective project. The individual who drinks the last water dies last. The group that shares the water finds more. Every hospital, every water treatment plant, every mutual aid network, every emergency shelter operating in a heat wave today descends from this principle. You survive heat not by being stronger than the sun, you survive it by being connected to people who will share the shade. The ancient humans who endured heat waves spanning centuries and millennia did not do it alone. Nobody does. The ones who tried are not our ancestors, they are the ones who vanished, nameless and unmourned, in a desert that does not remember them. Our ancestors are the ones who shared. If you want to see more videos like this, click the video on screen now and make sure to subscribe.